Okay. So, first thing I wanted to note is I'm gonna have office hours today from we'll say let's see. So I'll be done teaching my second class at around 2. So we'll say around 2 p.m. Uh, to 3. I'll send the YouTube link later when that's about to happen. So come ask any questions you have about course or about your homework, which like I said, I extended the deadline for your homework. I noticed that most of you had already submitted the homework, so if you're already happy with it, that's fine. If you wanted to revise or resubmit now that there's a longer deadline, then that's fine. It will automatically, you have like infinite resubmissions, so it will automatically replace whatever you submitted the first time. So you can always do that. The only thing is like if you resubmit late, then that will show up as like a late submission. But I think it still keeps track of you submitting on time anyway. So okay. So then today we're going to mostly finish up what's left of chapter 2 stuff. So well, I may take a little bit longer to go through some of Hilbert's axioms, even if that's not exactly what we're going to do um, going forward. So anyway, so I wanted to pay particular attention to this question from last time first. So we began by looking at parallelograms. So in particular for a rectangle, right, the association of the product AB to a product of lengths for the Greeks meant the area. So the product of two lengths was an area, not a length as we defined it. So this was the ancient Greek notion of how the product of two lengths was defined. And then to see what the corresponding notion was for a parallelogram, not a rectangle, we involved this idea of moving. There was some moving that we were allowed to do to cut apart, restructure this shape in a way that doesn't alter the area contained in the shape. And in doing this reassembly, we got a rectangle and came up with some notion of associating the same exact sort of thing. So it turns out that this area of parallelogram was also base times height, right? It's just that the fact that the parallelogram was sheared concealed what the height was, right? You couldn't read it off from the length of one of the slant sides. Okay, that was the big deal. Anyway, so and then our proof of what the area of a triangle was came from this this description of the area of a parallelogram. So looking at parallelogram or looking at triangle and doubling it in this way, which is another way of saying I take a triangle congruent to my given triangle and add it to it. And I add it to it. Again, it's an argument by motion. I take a copy of this thing and I move it in such a way that I've now constructed this parallelogram. This parallelogram has height denoted by this dashed line here or here. Of course, you might say, well, does the height change if what I consider my base is now this other length? And the answer is yes, it does. But it changes in a way that compensates for the other term. So I'll talk about that in a second when I focus on this formula again. So anyway, and we saw here that this is where the common notion comes in that things that coincide are equal. Okay, so what is meant by coinciding here are, for instance, two areas being equal. Okay, two areas coinciding, meaning existing in the same region. This is one notion of coinciding. Just like taking two lengths and matching them up is another notion of coinciding. Okay, so anyway, we saw that, summing the area of these two triangles now that I have is the area of the entire parallelogram, which led me to say that since these two areas coincide, they're actually equal. So then to find the area of a single triangle, I can divide by 2 here, which leads to this formula, that the area of a triangle is 1/2 base times height. Now, this has two important things here. So 2 things to note. So first, this is a statement about area, but it's also a statement about proportionality. So as a statement about area, what is being said here is that this is giving me area as a product of 2 numbers, but really, since product of 2 numbers arising from length is a rectangle, so this is giving me a rectangle. Okay, that is equal to the triangle. Okay, i.e. a rectangle with the same base and half the height of the triangle. Okay. Okay. Secondly, thing to note here is as a statement about proportionality, what does this say? Oh, there. So for triangles with the same height, the formula shows that the areas are proportional to their bases. Now, that might seem like a kind of trivial distinction to make from this very simple expression here, but it's that if you fixed the same height for triangles, then the area of the triangle is proportional to the base, right? So this is important for proving the Thales theorem. Okay, so we'll refer to this. Okay. So the thing is that this statement about proportionality works perfectly fine for us because we're willing to accept lengths that could be irrational. But for the ancient Greeks, as I've mentioned before, they didn't accept lengths that were irrational, and so this proportionality statement didn't quite follow immediately from this, and so actually Euclid had to devote a good chunk of Book 5 in the Elements to this theory of proportion. That reminds me, I'm also, I still haven't done it, but I'm going to post a copy of, like I said, an online copy of Euclid's Elements. I'll add that to the syllabus page soon, like later, a little bit later today, maybe during office hours. So anyway, this leads us immediately to, I want to use this fact to show the Pythagorean theorem. Now, maybe you've seen the Pythagorean theorem proved before, and there's a number of proofs of the Pythagorean theorem, and a lot of them are almost, many of them that you've seen probably involve some nice diagrams. And this one is no different, but the thing that I want to do is to use Euclid's original proof. So there are some other proofs that maybe are more straightforward to understand, especially with like an algebra background, than Euclid's proof. But Euclid's proof is really, really nice in the way that, you know, we're following how Euclid did things here. So Euclid's proof is actually really, really nice. So of course, you know, what is the Pythagorean theorem? You're familiar with the statement, you know, for if you have a right triangle with legs, you know, A and B, and hypotenuse C, then A squared plus B squared is equal to C squared. Now, the actual original statement of this is the following. So for any right-angled triangle, because we know the interior angle sum of a triangle is 180, if a triangle has one right angle, it can't have any more, right? So the second you say a right angled triangle, that fixes exactly one as the right angle. The sum of the other two then is together pi over 2. So the sum of the squares on the two shorter sides equals the square on the hypotenuse. Now, you could view this as just being kind of a quaint terminology here, since you know what they're saying when they say squares, right? But remember, they didn't have algebraic notation. So it's even better to actually see the picture. So what's the resulting picture look like here? So here's what it looks like. Okay. So here is what we want to prove. This is proof by diagram. I'm not going to write anything because these diagrams do the job. Okay. So this is Euclid's original proof of this. There are tons of proofs of the Pythagorean theorem. There's even a proof of the Pythagorean theorem that I might mention, and I might send an announcement with this link. So an American president, Garfield, I think, actually gave a novel proof of the Pythagorean theorem using the area of trapezoids. So so I might provide a link to that. That's, you can look that up. It's pretty funny. But anyway, so there's tons of ways that this can be done. This is Euclid's original way of doing it. So here's the picture. I start with right triangle here in the middle. And so once I've begun with this right triangle, I consider the squares, okay, on each of these sides, right? And so we construct the squares on each of these sides. Of course, the area, these shaded regions, the area of these squares is given to me by, so if this is side length A, then this, or this, if this, yeah, so if this side has length A, then the area of this square is A squared. If this side has length B, the area of this darker shaded square is B squared. So what I want to prove is that, you know, this light gray rectangle has the same area as this, or sorry, this light gray square has the same area as this light gray rectangle here, which is a part of this square on the hypotenuse, and this dark gray square on the other side, the longer side here, has the same area as this dark gray rectangle on the hypotenuse. Okay, and if I have done that, then by our arguments of areas, right? So this area C squared is going to be B squared plus A squared. Okay, directly here is what this statement is. So if this is true, this rectangle being shaded in this way means that C squared is A squared plus B squared. Okay. Now, in order to prove this, I begin with looking at half of this light gray square. Okay, so I look at half of this light gray square, and ultimately I want to show that half of this light gray square is equal to half of this light gray rectangle. Okay. then repeating the argument for the missing triangle, right? Half of this light gray square is a triangle. If I repeat the argument for the missing triangle, then I get the missing triangle in this rectangle here that I'm pointing at. And so I get that the light gray square is equal to the light gray rectangle in area, and then the dark gray square is equal to the dark gray rectangle in area by a similar argument, and I'm done. Okay, and so let's go through this step by step. So here, I start with this half of this light gray square. Okay, there it is. So then next, I claim that this area involving half of the light gray square is actually equal to the area of this triangle. Why? Well, they have the same base. So if this is my base of this triangle in the second step has the same base, and I claim has the same height. Well, this triangle is a right triangle. So here is its base, and here is its height. This second triangle, here's its base, but where's its height? Its height is actually still this. Right? Remember that the height is determined as the height of a parallelogram formed by doubling this triangle, right? Okay, so my height is actually still this length. Okay, and so using that formula for the area of a triangle, these two triangles have the same area, and since they coincide in area, they coincide, they are equal, right? Okay, so I've moved on to this triangle. So now what do? Now I divide my right angle. Okay, this can be done by bisecting my right angle. So if I bisect my right angle like this, I get a perpendicular. So I drop this perpendicular in this way. Sorry, I don't need to do that. I just need to drop the perpendicular through this point. Okay, so if I drop the perpendicular through this point, okay, that is the other vertex, right? The vertex where the right angle is in my triangle. If I drop the perpendicular there, so I draw this dashed line, I want to consider this triangle. Okay. Okay, so then this included triangle is congruent to what I started with, not using an argument about the area of the triangle, but they're congruent by side angle side. Okay, they're congruent by side angle side. So how is that? Well, so this triangle has this side length. This triangle has a side length which is another side of the same square. So those two are congruent. Okay. This triangle and this triangle have two side lengths that are they are different sides of the same square, and so those sides are congruent. And then the included angle here is the sum of that angle of the triangle and a right angle. But it's that sum in both steps, right? So in this part of the diagram, this is right angle plus the angle there I'll call beta in my right triangle. Here I have beta plus a right angle. So in both cases it's beta plus a right angle. So side angle side is satisfied, so these two triangles are congruent by side angle side. Okay. And then the very last step is again using an argument about area, or about using the formula for area of a triangle. This triangle and the triangle in the last step have the same base and the same height. So they have the same area, and so those things coincide. So then 1/2 of this square is 1/2 of the light gray square is 1/2 of the light gray rectangle. So the light gray square is equal to the light gray rectangle. Similarly for the dark gray square and dark gray rectangle. And so the square on the hypotenuse is equal to the sum of the squares on the other two shorter sides. And that's the Pythagorean theorem. Okay. So that's how that goes. This was Euclid's proof of the Pythagorean theorem. Okay. Now, I want to bring your attention to something that I will mention in a later section. So this figure, I'll call figure star here. So, or I'll just call it by its name in the textbook. So figure 2.13 gives a natural way of constructing a square equal in area to a given rectangle. Okay, so this is kind of one of our first examples of one of these sorts of questions about composite straight edge construction. So construct a given figure that has a specified area that is given to you, by the area of some other figure. Okay. All right. And so, what is the way that I go about doing this? So given i.e., given the light gray rectangle, oh, this should be an A, I guess. Given the light gray rectangle, construct the rest of that figure. So that is, imagine I give you only the light gray rectangle, everything else in this figure is deleted. Construct the rest of the figure, okay, from that. If you can do that, then you've constructed a right triangle that has, you've constructed, the right triangle that has the required components, but also the most important thing we're trying to get to is constructing a square that has the same area as this rectangle. Okay. All right. So what is the way of doing this? Well, extending this light gray rectangle to be the rest of this square is easy. That's something I can do. That's no problem. Then the point is trying to construct this right triangle. Okay. So how do I do that? So if I'm trying to do this, I have light gray rectangle. I can extend that to be this square here that I'm outlining. Okay. But once I've done that, to construct the rest of this figure, the next thing I have to do is construct this right triangle. So how do I do that? How do I construct this right triangle? There's a method we're going to go over for doing this that is very, very nice, and it always works. But try to think about how you would construct this right triangle, because you need its other vertex. You have its hypotenuse, basically, is what you have here. So you need its vertex to line up that splits these squares in this way, right? You can't just pick it. You can't just pick any point here. You have to be careful with how you construct that. So we'll see how you can do that in a way that reproduces that whole figure. Okay, so I don't see any questions about that. So let's consider our proof of the Thales theorem. Okay, so proof of the Thales theorem. Well, before I can talk about the proof of the Thales theorem, maybe I should restate it. So the Thales theorem which is a line drawn parallel to one side of a triangle cuts the other two sides proportionally. Okay. So let me draw a picture that I'm going to be referring to for the rest of this. So let's consider the following triangle. Maybe I'll Okay, so here's triangle. We'll say this is a triangle ABC. And let's consider this triangle cut by a line that is parallel to BC. Okay, so I get line segment, say PQ, from this. Okay, and what I want to draw here are the line segments connecting the vertices B to Q and C to P in this way. Okay. All right, so here's the triangle I want to consider. Now, what do I want to say? So first, note that since PQ is parallel to BC, okay, the triangles PQB, so PQB, and PQC, so PQB and PQC, these two triangles here, on base PQ have the same height. What height is that? That height is the distance from PQ to this parallel BC, i.e. the distance between the parallels. Okay. So they have the same base, they share a base, PQ, and they have the same height. Thus, they have the same area. Okay, thus they have the same area. Okay, now, consider triangles APQ, which is this top triangle, right, and say PQB. And PQC here. Okay, but I'm going to do this one at a time. Okay. All right. So if we add PQB to APQ, so if we add triangle PQB to APQ, we get the triangle AQB. Okay. If we add PQC to APQ, we get triangle APC. Okay. But we're adding equals to equals, right? So we began with two triangles PQB, PQC that have the same area. And when we say add here, we're adding the areas of these triangles. So we're adding the areas of PQB to APQ and PQC to APQ. So we're adding two areas that are equal to APQ. It's equal to itself. Okay. And what we get are two different triangles, AQB and APC. But those two different triangles then have to actually have the same area because we've gotten those areas by adding equals to equals. Okay. All right. Thus, triangles AQB and APC are equal in area. Okay. Now, consider triangle AQB. All right, first. So, let's move over here. I will be swapping back and forth for my diagram's sake from this sheet to my picture. Okay, so consider the two triangles that make up AQB. So consider the triangles APQ and PQB that make up AQB. Okay. All right. So that is APQ and PQB. So both of those have bases, okay, that lie, say, on the line AB. Okay. Relative to this base on the line AB, they have the same height. Okay, that is the perpendicular distance, say, from Q to this, from 2Q from the line AB. Okay. Thus, their bases are in the ratio of their areas. So here's where that statement on proportionality from the area of the formula for area of a triangle comes in. Okay, so let me write that out. So here, relative to their bases on the line AB, these triangles have the same height. That height is the perpendicular distance to Q. Okay. All right. Thus, by our formula for area of a triangle, and rather than just that formula, but that statement we mentioned on proportionality following that formula, their bases are in the ratio of their areas. What this comes from is, remember we said considering a fixed height, right? The proportion of the bases, or the bases were proportional to the area, right? So fix a height between two triangles, the bases had to be in the proportion of their area, because the only other thing left in that formula was the base, right? So what this means then is the length of those bases is, say, AP, the length of AP over the length of PB has to be equal to the ratio of the areas corresponding to these. So the area of triangle APQ divided by the area of triangle PQB. Now let me bring back my diagram. So bringing back my diagram over here. So I have base AP, right, and base PB. So that ratio has to be the same as the ratio of the area of APQ and PQB. Okay, this is again directly from that formula, or rather the statements following my triangle area formula. Okay. Now, we could have actually done it the other way, right? Now, similarly, using the same argument with triangle PQC instead. I get a similar statement that the length of AQ over QC is equal to the area of APQ over the area of PQB, or sorry, PQC, sorry. But the area of PQB and the area of PQC are equal. Right? That's what we said here. So the areas of PQB and PQC are equal. APQ is, the numerator here is the same. Thus, the length of AP divided by the length of PB is equal to area of APQ over area of PQB, but this is equal to the area of APQ over the area of PQC, which is the length of AQ over the length of QC. But that's the Thales theorem. That's it. That's exactly what we wanted to show. Okay. All right. So that's that. So now we've tidied that up. The Thales theorem is something that's very, very useful for us, and we had mentioned it and even used it earlier. And so now to close that circle into something that actually makes sense, we've proven the Thales theorem now that we have this understanding of areas. Okay. So we have a couple more things that we want to say here. So next thing I want to talk about are angles in a circle. Okay. And so what do I mean by this? What's rather, I should say, the main thing I get out of this? So the first thing I want to mention is the invariance of angles in a circle. I'm going to use the word invariance a lot in this course, so you'll see exactly what I mean in this context. So invariance of angles in a circle. That is, if A and B are 2 points on a circle, then for all points C on one of the arcs connecting A and B, the angle ACB is constant. What does that even look like in picture? Okay, well, what do I even say here? Okay, well, in this picture, say that I have selected points A and B. Okay, so I select points A and B, and then I pick C wherever I want. So I pick C wherever I want, either on this arc or along this arc. What this is saying is that this angle, ACB, is the same. It doesn't matter where I've selected C, that measurement of that angle is the same. So if I had an animation of this, if I take C and I would slide it around this circle, this angle is remaining fixed. Okay, this angle, ACB, is remaining constant. Well, how can I prove that? So I actually have everything I need for the proof here. So what do I do here? So one, I draw in lines from A, B, and C to the center. So I draw in these center lines. Okay. So after I draw in those center lines, I get these two triangles here. So I can connect A to C, C to B. I don't need to connect A to B. So I get these lines here. Now these three lines split these angles at my center of the circle O into the following pieces. So first I have to label some things. So if I label this angle at A, alpha, and this angle at B, beta, then what do I know about the angles here at the origin? Well, what I get is that these triangles that I formed here are isosceles triangles, right? So these are isosceles triangles. So ultimately, this follows from the isosceles triangle theorem. Okay. So going back to my picture, I have points A, B, and C. I have my center of the circle. These lines that I've drawn in are all radii of the circle, so they all have the same length. Okay, they're the radius of the circle. Well, that means that the triangle AOC is an isosceles triangle. The two sides that make it isosceles are AO and OC. Similarly, BO and OC are the same as well. So I get two isosceles triangles, which means that if I've called this angle at A alpha and this angle at B beta, then by the isosceles triangle theorem, these other angles of these triangles have to also be alpha and beta here. Okay? And so what this means is that I have in this triangle beta plus some other angle is pi. And in the other triangle, alpha plus some unknown angle has to be pi. But that just means that this angle is pi minus 2 alpha. And this angle is pi minus 2 beta. Now, since a single point has 2 pi worth of angle, then the remaining piece is 2 times alpha plus beta. But this angle, 2 alpha plus beta, is constant. This diagram, it doesn't matter where I put C, this angle is always 2 times alpha plus beta. So if that's constant, then alpha plus beta has to be constant. But alpha plus beta is the angle at C. And that's it. So what's the most important thing here? So from that diagram, the angle AOB is 2 times alpha plus beta and is constant. But of this, if 2 times alpha plus beta is constant, that is, alpha plus beta is constant, i.e., the angle at ACB is constant, or I don't have to say at here. The angle ACB is constant since it is alpha plus beta. So let me give you a close-up of this diagram in case the picture was not that clear before. So here's the diagram, in case you're watching this later and want to pause here. Okay, that's what it looks like. Okay. All right. So this gives me a very nice fact. So here's fact 1 about angles in a circle. Here's fact 2 about angles in a circle. So a nice special case follows. So what does the special case say? So this is called angle in a semicircle. Theorem. These theorems are very creatively named, right? That is, if A and B are the ends of a diameter of a semicircle, or of a circle. You can pick either the top or the bottom or left and right half, however your diameter is, right? You can have the diameter oriented however you want. So if A and B are the ends of the diameter of a circle and C is any other point on the circle, then ACB is a right angle. Okay. How is this a special case? The following. It's the special case when alpha and beta are equal. Okay. So when alpha and beta are equal, that's the special case we get. So this is neat because when you look at the picture, what this says is that whenever you have this configuration, A and B are 2 endpoints of a diameter of some circle. So we'll just look at the top semicircle here. Wherever you pick C to be, right, gives you a right angle. Okay, forms a right triangle here if you draw in these connecting line segments. Okay, and so this gives a very, very nice way of answering the following question. Given a hypotenuse AB, how do you construct a right-angled triangle whose other vertex C lies on a given line? So pretend that I didn't have this picture here, okay? So pretend the only thing in this picture I have are my line segments AB and some given line, this dashed line here, okay? So think about extending that all the way. And the question I have, construct a right triangle that has AB as its hypotenuse and its other vertex lies on this line. Thinking of how you might do that it could be kind of tricky without this fact, but this fact makes it really easy. You just look and see where that line intersects the semicircle that has that AB length as its diameter, and that's exactly what you get. Now, how would you construct this fully with compass and straight edge? So with compass and straight edge, you would start out with your AB segment, okay? So you start out with your AB segment. How do you construct the circle or the semicircle that has that AB segment as its diameter? Well, you need to be able to draw a circle, but to draw a circle, knowing the diameter doesn't help me. It's knowing the radius is what I need. But how do I find the radius from the diameter? Well, I need half of the diameter. Well, how do I get half of the length of a line segment? I bisect it. So I would start by bisecting the line segment. So I'd bisect AB. That would give me the radius of the circle. And then I would draw the circle, and then I'm done. I've constructed the semicircle that has AB as its diameter. Okay? All right. And so this actually allows us to do the following. So this allows us, recall, I had this question. What if I began with a rectangle here? So I began with the lightly shaded rectangle here, and I want to construct a square having that having the same area as the starting rectangle. How do I do that? The steps for doing that is I take my rectangle here, I extend it to a square. Okay, so I take that rectangle, extend it to a square. Once I've extended that rectangle to a square, I now need to construct a right triangle, okay, that has its hypotenuse on this square that I've created by extension, and its third vertex lies on this dashed line that I get from the division of this square. Okay, so then in order to do that, I need to construct the semicircle, right, that has that square length as its diameter. Okay, so doing that yields this exact right triangle, and I've constructed this diagram entirely, so I've picked out my square. That's the way to do this. So this provides a really, really nice way of doing that. Okay, now I've run out of time before doing this absolute last section in Chapter 2, so it's fine. We'll finish that on Monday together with a discussion of Hilbert's axioms, so which I think are interesting enough to talk about now, and then we'll see how this corresponds to some stuff that we do later. But anyway, so I think that's the idea here. I think that's pretty much all I wanted to say today, since I'm already out of time. So like I said, I'll post an announcement later today for office hours, and you're encouraged to come and ask any question that you might have about the homework or just about class material in general. So over the weekend I'll post another homework assignment, and I'll post like I said, a copy of Euclid's Elements that you can have a look at. It even has like draggable diagrams and stuff. But anyway, I will see you all on Monday.